Hello, this is Michaela Fenwick, and I am recording my Unit 2 presentation. I apologize ahead of time for my voice. I've been sick, and my voice has still not quite come back, but I'm going to do my best. This is the data that we were given for analyzing and mapping genes. These are the offspring. And the first step is just to arrange them in a data chart like I've done here. These are not in any particular order. These are just as they were given to us. The first thing I like to do is rearrange them in order of frequency so that I can more easily see which are the parental types and which are the single crossovers and double crossovers. The next step is to determine the parental types and the double crossovers. It's easy to quickly identify which are the parental types because they're more abundant. So we can see here that plus, 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 and ABC are the parental type because they have the most individuals in the offspring. Similarly, it's easier to identify the double crossovers because they are least abundant type. So here we see plus BC and A++ are the double crossovers. Once you've determined which is the parental type and which is double crossovers, it makes it easier to figure out which gene is in the middle, which is the next step. You can see here, this is the parental type, and these are the double crossovers. And if you look at this, you can see that the BC part of this double crossover is the same as one of the parental types, and the plus plus part of this double crossover is also the same as one of the parental types. But the difference is here, where we have the A and the plus switched. If you look at the double crossovers, you can also think of it this way, where you see that this plus B part does not match this parental type. And in the same way, this A plus part does not match a parental type. So since plus B and A plus don't match either parental type, we can tell that A is where the difference is. So the gene in the middle is A. And once we've determined that the gene in the middle is A, I like to rewrite all of the types here just for ease of reading so that the A's are always in the middle. Otherwise, I get confused about which one is which and where things are supposed to go. So I've rewritten this frequency chart with the A gene in the middle, since that's where it belongs. The next thing to do is determine the distance between genes, and you can do that by looking at the single crossovers. In this case, I'm looking at the red single crossover first. You can see that to get BA+, if you line up the parental types, you have to go from B to A, and then here's the crossover between A and C. In the same way, you've got plus plus C, you go across, and then the crossover is right here between A and C. So we know that when we're looking at this red single crossover, we're looking at the distance between gene A and gene C. In order to find the distance, you add up the number of individuals that there are and then divide by the total. So I've got 1010, 970, and then this is the double crossovers, since those also include this cross from A to C, and then divided by 5,742, which is the total number of individuals. Using that formula, the distance is 0.387. I multiplied here by 100 to convert to centimorgans or map units. So we can say that the distance between A and C is 38.7. In the same way, you want to figure out the distance between gene A and gene B. I'm looking here at this green single crossover. You can see that to get plus AC, you would have to come here and go plus and then cross over to A, and then here's C. In the same way, to get B++, you'd have to go B and then cross over to plus, and then here's the other plus. So we know that when we're looking at this green single crossover, we're looking at the distance between B and A because that's where the crossover is located. Same thing here. To find the distance, we add up the number of individuals. So we've got 420 plus 400 plus the double crossovers again. And we're going to divide by the total. our distance in this case is going to be 0.185. And here again, I've multiplied by 100 to get map units. So the distance between B and A is 18.5 map units. The next step is just to draw the map. Since we know which gene is in the middle, this is fairly easy to do. Here I've got A and B with 18.5 map units between them, and A and C with 38.7 map units between them. The next thing we will want to know is the coefficient of coincidence. So we can see how much interference there is for the double crossovers. To calculate the coefficient of coincidence, you first have to know how many double crossovers you would expect to have if there had been no interference at all. So in order to figure that out, I've multiplied the distance between A and B times the distance between A and C. And I put this 100 in here. You could convert this to a percentage if you wanted to by multiplying by 100, but I'm not going to. We can say that 0.0716 of the total offspring should be double crossovers if there's no interference at all. So I've multiplied that by the total number of offspring. And here you can see that we would have expected to have 411 double crossovers if there had not been any interference. And you can see that the actual number of double crossovers we had was smaller than that. We only had 240. So the coefficient of coincidence then is the number that we actually had divided by the number we would have expected to have if there weren't any interference. In this case, the coefficient of coincidence is 0.583. So what this means is that about 60% of the expected double crossovers actually occurred in our sample. So clearly there was interference. Otherwise, 100% of the double crossovers would have actually occurred. We can calculate the interference by just subtracting the coefficient of coincidence from 1. So the interference in this case was 0.416 or 41.6%. This is a positive number, so we had positive interference. And about 41% of the double crossovers we would have expected did not occur in this case because of interference. So that wraps up my presentation on gene mapping, and I hope you enjoyed. Thanks.